Namaskar and welcome back to the course on statistical mechanics of phases and phase transitions. We have studied a lot about the Ising model and variety of other classical problems. So today we are going to start a discussion on quantum systems. So since we are starting a new topic, it might not be a bad idea to sort of collect all our ideas that we have learned in the course so far. So the main concepts we have seen is that phases occurs when phases arise when many degrees of freedom interact with each other, and you can have continuous phase transitions between these phases, and these phase transitions have universal properties. We use models, carefully constructed models, to study the physics of interest, and symmetry becomes a very important concept that is necessary and useful to build models. So interactions between the degrees of freedom are essential for forming different phases, and these phases can oftentimes be characterized by a broken symmetry and an order parameter that is a proxy for the broken symmetry. So we used the interacting particles model to show you a paradigm of doing a set of calculations starting from microscopic degrees of freedom, computing a phenomenological free energy, and from there deducing phases and phase transitions. And we even obtained critical exponents, which unfortunately did not match with experiments. We then moved on to the Ising model. The Ising model was very useful in a variety of different ways. We could see a clearly broken symmetry phase in the two-dimensional Ising model, for example. We could learn about variety of conceptual and technical tools. In particular, conceptually, we learned about this importance of spatial dimension. So we noticed that in one dimension, the Ising model did not have any broken symmetry phase at finite temperature, whereas in two dimensions there were two distinct phases and there is a phase transition that separates them. We learned about the notion of duality, which is very important and useful concept in physics. And we learned a variety of other technical calculational tools like the transfer matrix, series expansion methods, and so on. So this is how far we have come in the course so far. And it will be interesting to see how these ideas that we have seen in mostly in the classical context can be translated to quantum problems. So that is what we are going to do in this chapter. In this chapter, we are going to discuss a variety of systems. We will focus on Ising-like systems, but with some quantum mechanics included. So we will start with the simplest possible quantum system in this lecture, and this is what we call a qubit. But before we do that, I would like to present to you a broader motivation for studying quantum problems. So as all of you know, this is the era of quantum information processing. So we hear almost every day that there is a certain advance in quantum computation, there is new hardware that is better, and so on. You keep hearing these things. And the main idea there is you want to create quantum systems and you want to have the ability to control the quantum systems reliably to produce certain information processing in an error-free way. Okay, and ultimately we would like to have a general purpose quantum computer. That may be a little ways off, maybe, may not be, I don't know. But this is one of the goals. So you can see that studying, whatever you make will be in contact with the environment, and therefore you have to study its thermodynamics, and so it's very important to study the effects of quantum computers, etc. Now, quantum computers, as you know, work with qubits, and qubits are two-state systems, and we will explore a simple example of such a system. So this motivation appears to be sort of directed towards people who are taking up these kind of problems for certain applications. But the quantum problems also offer new conceptual directions in physics. One of the main thing that happens in quantum systems is that you can have zero temperature phase transitions. Now, what do I mean by that? So here's an example. So this is a certain material. I don't want to get into the details of this. You can look at this paper if you're interested. But what happens here is, experiments are of course done at finite temperature, but you can extrapolate down to 0. And you see that there is some nail phase. Nail phase is, remember, the antiferromagnetic phase, which upon a magnetic field melts, in the sense that it sort of undergoes some kind of phase transition at 0 temperature and goes to some other phase. So remember, if I am going along this line, temperature is 0, yet I am driving a phase transition. So usually we think in terms of phase transitions being driven between competition between energy and entropy. Certainly this is what we saw in the case of the Ising model and so on. Well, what is entropy here? Because we are at 0 temperature. Right? So that's an interesting question, and this is definitely worth exploring. And so what happens here is that these phase transitions are produced by what are called as quantum fluctuations, and we will actually see what this means as we go along in this chapter. Okay, and I have to mention this because it is very important. Although we will not have a lot of time to discuss these things in this course, quantum entanglement, the entanglement between many degrees of freedom in the system, that plays a very critical role in these quantum phase transitions. So when you drive a quantum phase transition, the nature of entanglement on one side will change to some other pattern of entanglement on the other side. So there's a certain pattern of entanglement here, and there's certain other kind of pattern of entanglement there. So these are all very interesting topics and very active areas of current research, but this is definitely a topic for another course. Okay, so having hopefully motivated you to look at quantum problems, let me start discussing a very specific quantum model which is essential for all the discussions that we'll have in this chapter, and this is the problem of a qubit. So what is a qubit? At a very simple level, a qubit is a quantum system with two linearly independent states. So in other words, if the Hilbert space of the quantum system is denoted by V, the dimension of V is 2. Remember, V is a complex vector space. So the dimension of V is 2. This is what we mean by a qubit. Now you can realize qubits, physical qubits, in many different ways. I will not get into the details of that. Okay, so we have got the kinematics of the qubit fixed. What we mean by that is any state of the qubit can be described by two linearly independent states, linear combination of two linearly independent states. Now you can have operators on this vector space V, and they could be, we could use them as observables and whatnot. So if you look at what are the operators, all possible Hermitian operators can be described by linear combinations of these 4 matrices. One is of course the identity. The X operator is the Pauli X operator. The Y operator here is the Pauli Y, and the Z is the Pauli Z. And this little I here, that is square root of -1, which is the purely imaginary number. Okay, so now what we'll do is we'll choose a basis of V which are eigenstates of the Z operator. This is definitely a convention. It's a very common and very universally used convention, so you might as well use it yourself so that you can have conversations without confusion with your colleagues. So these states, the basis states, are labeled by S, where S is the eigenvalue associated with the Z operator. So S equal to +1 will give you eigenvalue +1, and that state we call as also up state. Particularly if you come from a condensed matter background, you would call this an up state. And the negative state is called a down state or a -1 state. It's also called 0 and 1 in many quantum information type literature. Okay, now all of you have studied elementary quantum mechanics, so you know that these x, y, z operators have certain commutation relationships. So if you commute the operators x and y, you will get something imaginary number times I times Z and so on. So you are familiar with that. And apart from these, it will turn out that the following relationship between the operators, I am showing you just examples of some of those, is that any of these operators, if you square them, you will get identity. That's a very important and useful thing to remember. It's easy to prove, but it's still important. And then you will see that these operators x and z, they anti-commute. So if I take x and z, and xz plus zx will be 0. Now any two different operators here between x, y and z will be anti-commuting. So this is somewhat less commonly discussed in elementary courses, of course discussed at length in advanced courses. Okay, so we continue our discussion of the qubit. So I need a Hamiltonian on the qubit space. So what I am going to do is, I am going to think of using one of the Hermitian operators, and I am going to write down a Hamiltonian which is minus little h times x. So naturally h has units of energy scale, and please note that h is not the Planck's constant. Okay, please remember that little h is something like what we will call as a transverse field. Why is this called transverse field become clear as we discuss in the next chapter. Very quickly, the qubit is sort of thought of in the up and down state, which are the eigenstates of the z operator. So this can be thought of as a magnetic field transverse to the z direction. So that's some slightly simple way to think about this. Okay. So now I claim that this Hamiltonian implements for you a Z2 symmetry, an Ising symmetry on the qubit. So what is this Ising symmetry? So the symmetry operations are described by identity, which is the identity operation, and by a unitary operator x, the same x that entered the Hamiltonian. So you can see that under this unitary, x dagger is equal to h. So you immediately see that this model has an Ising symmetry. Okay, now we want to keep this quantum system in thermal equilibrium, and we will be explicitly focused on thermal equilibrium systems in this course. So thermal state at a temperature T is described by a density matrix. So this is defined by some matrix on the Hilbert space. It's a Hermitian matrix, and what it does is it gives you the thermal distribution, the Gibbs distribution function over the states. So it can be written in this fashion, where the partition function is trace e to the minus beta h. H is this Hamiltonian here. Okay, now I will welcome you to do these calculations. You can show very quickly without too much trouble that for h greater than or equal to 0, we have that z, the partition function, is 2 cosh beta h. So remember, beta h is a dimensionless number, and the density matrix you can show by, again, by simple algebra, that if you just exponentiate, if you put this quantity here, you will get beta h times x. You can show that that is equal to this quantity. So you see, this is the density matrix. Now as expected, this object depends only through the coupling constant, dimensionless coupling constant h tilde beta h. And you can see again explicitly by computation that Z2 symmetry is never broken in a qubit at any temperature, because you can see that the density matrix is invariant under in this flip transformation described by this x operator. So this is not surprising based on our discussion, because remember, we said that if you want to break symmetry and if you want to hold on to some phase with order parameter and so on, then you need to go to the thermodynamic limit first. But this is just 2 degrees of freedom, or let us say, I am putting it crudely, this is a 2-dimensional Hilbert space. So it is a few degrees of freedom. So you see that you do not expect any breaking symmetry and things like that. So this is not an unexpected result. In fact, we should be relieved that it is not breaking symmetry. Okay, you can actually formally prove that it doesn't break symmetry. What you can do is you can apply a symmetry breaking field. So to this you add minus HB times Z. Now if I put Z, you will see that it will break symmetry. X transpose HB, X dagger will not be equal to 0. And then you can find out what is the density matrix, and then you can let HB go to 0 and you will be able to show that that will exactly recover this row. So please try that. It's an interesting and useful exercise. Okay, so we have worked this out and we can now compute any observable because we know the density matrix. So you might think it's kind of a boring problem. But if you leave it at that, then of course you will miss a whole lot of things. So what we are going to do is we are going to take a closer look at this result that we have. So first is we would like to recover some thermodynamics. So suppose I have this qubit in equilibrium. What would be its specific heat? If I want to heat up the qubit, how much energy should I give it? So if you just work this out, you will see that the specific heat looks like this. It's just h by t sec h by t, the whole square. But now you should be a bit surprised. Have you seen this sort of thing before? Does it look familiar to you? Just pause the video and see if you have seen an expression like this before. Okay. So let's look at another interesting observation. So you see this rho is e to the minus beta h is proportional to this. I am just suppressing the factor of partition from here. It is not important for the current discussion. So have we seen any expression like this in quantum mechanics before? Now if I invite you to take this minus sign and write it as minus square root of minus 1 whole square, then you will see that this can be written as e to the minus I, and this expression in the bracket here looks like a time. You see, e to the minus I ht is the propagator, or it is the operator that translates in time. It tells you the propagation of the quantum system. So now you see that this density matrix strangely looks like propagation in what is called as imaginary time, right? So is this an accident or is this something deep? Well, I don't know. What I am going to do is I am going to use the fact that it looks like this and try to extract some stuff out of this observation. So I am observing the fact that this looks like propagation in imaginary time, and I am going to use that idea to get somewhere. So I might sound a little cryptic here, but you will see that this will get interesting as we proceed. So just come along with me for the ride. You imagine that there is something called imaginary time tau, right? Tau is typically called the imaginary time, but remember tau is a real number. So what I can do, just like I did for e to the minus beta h, I could define this imaginary time propagator for any tau, okay, real. Now what I do is I notice that the partition function is trace of u, this propagator, evaluated at beta, okay. Now I remember that the trace, because my qubit has two linearly independent states, actually orthogonal states, spanned, the vector space is spanned by these two states which are eigenstates of the Z operator. I can write out the trace explicitly as sum over these states S, the matrix element of e to the minus beta h between the two states S, okay. But what is this quantity? So that quantity has a very nice interpretation in elementary quantum mechanics. It tells me that it is the quantum amplitude that the system starting at state S at tau equal to 0 at 0 imaginary time reaches the state S back at an imaginary time tau equal to beta. So this can be interpreted as the imaginary time amplitude of starting from one of the eigenstates of the z operator and coming back to the same eigenstate of the z operator at imaginary time beta. And remarkably, you can interpret the partition function as the sum over all such amplitudes. So you have a basis state for your Hilbert space. You ask what is the amplitude of starting from one of the basis states and coming back to the same basis state, and sum over all the basis states. That turns out to be the partition function. We know the partition function exactly. We solved it in the previous slide. But we are reinterpreting the partition function, and we are going to make use of this observation to try and make certain connections. Okay. So let me continue. Now, this whole business was discussed as if, okay, I'm starting at tau equal to 0 and then coming to beta and reaching the state back at time beta. So there is some finite interval of time. Now I could, instead of making this sudden like transition from 0 at time t equal to 0 to beta, wait for beta time, I could take steps to reach beta. So what I'm going to do is, I'm going to take small steps. So I'm going to introduce a discrete number n tau, which is the number of steps I'm going to take to reach beta. So what will be the time interval between each steps? It will be delta tau, which will be beta by n tau. Okay, why am I doing this? I'm going to label the times that I will like a tick, clock tick from 0 to n tau minus 1. So that means when I'm at 0, I will be at time tau equal to 0. When I'm at L equal to 1, I will be 1 times delta tau and so on. And after L steps, I will be at the imaginary time tau with subscript L, which is L times delta tau. Okay. Now, I am just going to say, I have a e to the minus beta, which is a simple exponential of a single operator with a number here. Everything is commuting with everything else. So what I can do is I can take this beta here and break it up into little delta taus like I did here, and I can take this exponential, and since every h here commutes with every other h, I could just write it as a product of e to the delta tau h. How many such terms will be there? There will be n tau terms, and n taus are labeled from 0 to n tau minus 1. Okay, so this is what we have done. Okay, very nice. Now what we can do is we can put this expression in the partition function, and you see I'm summing over all states. I'm starting at S, and instead of putting e to the minus beta h directly, I'm doing, first time I do a little propagation by little delta tau h, then I do a little bit with another delta tau h and so on, and I reach here. So from here to here, it's just saying that this full step of beta can be taken in n tau steps. That's it. So remember, these are this is an operator, this is an operator, this is an operator, this is an operator. So we start from here and we just multiply operators to the left, and we find the amplitude of the final state that we get. With the final state we want the amplitude for is the same state that we start off with. Okay, now you realize that this can be given a different meaning as the amplitude of going from some state to some other state is the sum of amplitudes over paths. That means for going from one state to the other, there is a path, and what you can do is you can sum over amplitudes of each path, and this is the Feynman path integral idea. And I will show you that this expression can be used to get an analogous thing in the context of our problem. So this is what I do. I start at L equal to 0, and this is L equal to 1, so it's tau 1, and I have this operator and so on. So between, now these dots here are not they are like time. These are like time, different time instances, discrete times. What I'm going to do is, between this operator and the next one, I'm going to introduce a partition of unity. What I'm going to do is, I'm going to introduce a complete set of states. And so, for example, if I'm at the lth tau L, that is, if I'm at tau L, here I introduce identity operator on the Hilbert space at the lth time site, and that is written as sum over SL equal to plus minus 1, this projection operator onto the SL. Okay. Now, what I can do is, remember, I started off with the state S and ended at state S. So, what I can say is that this S is same as S0, and whatever is happening here, which at the end tau time point, is same as what is happening at tau equal to 0. So, with all this done, I have introduced the complete set of states in between, and I end up with an expression like this. So, this is a matrix element of going from S0 to S1, S1 to S2. So, that the journey from S0 back to S0 is done by first going to S1, then going to S2, then going to S, and so on. So, this is the statement of sum over amplitudes of paths. So, this describes various different paths of going from S and ending up with S itself. We now call S equal to S0 and coming back to S0 itself, and you can have many different paths possible here. So, these are small amplitudes, small meaning amplitudes over these small jumps, and they are products of them. So, what I can do is I can collect them and I can write them as product of matrix elements in this fashion. And what do I have to do to get the partition function? I sum over all possible configurations of SL. Remember, at every point I had plus minus 1. So, you can sum over all the plus minus 1 states that you have put in between at all sites, and if you have n tau of them, there will be 2 to the n tau such states, and you can just sum over all of those. So, that is what I get. Okay, where do I go from here? So, now I notice that this object are elements of a 2 by 2 matrix. So, this e to the delta tau h is a 2 by 2 matrix, and we have seen this before when we solve the partition function. So, delta tau h is cosh delta tau 1 plus sinh delta tau h x. Okay. Now, what I do is I take this object and I write out the matrix element. On the left side it can be plus or minus 1, on the right side it can be plus or minus 1, and I just write out the matrix elements. So, I get this very nice looking matrix. Okay. Now, I stare at this matrix a bit and I realize that this matrix can be written by taking out a common factor, the following thing: e to the k, because these two are the same, and e to the minus k, e to the minus k. So, what is this k? This k can be solved for using delta tau h by this expression. Okay. But suddenly you realize that this looks like the transfer matrix of the one-dimensional classical Ising model. So, what I am showing you here is that the matrix element from L to the amplitude from going from SL to SL plus 1, which is the matrix element that is shown here, is equal to some factor times the transfer matrix. So, the amplitude is same as the transfer matrix. That is the matrices of the amplitudes are same as the transfer matrix. That is what we are showing here. Okay, and because of this we reach an astonishing conclusion. So, let me walk you through this. So, I am computing the partition function of the qubit kept at a dimensionless parameter beta h. We know the exact answer for this. I showed by a set of arguments that this can be written in this form, right, using interpretation of the partition function as an amplitude of propagating in imaginary time, and I slice up the imaginary time into little bits. And then I was able to reduce that to something that looks like a transfer matrix. And now what I do, this factor I pull out from every time slice. So I will get this term to the power n tau. Okay, what am I left with here? That is the product of all of these things, which I can now exponentiate and sum. Product of exponentials is exponential of sums. And I can get this, and you see that this is exactly the partition function of a 1D classical Ising model at a coupling constant k. What is k? Remember k was related to delta tau h. And so we have found a absolutely stunning result. The partition function of a zero-dimensional quantum system with a coupling constant beta h is related to the partition function of a one-dimensional classical system at a different coupling constant k, which is determined by the coupling constant of our original quantum problem. Okay, so this is a remarkable result. So you may wonder, like, so why would this be interesting? Okay, so before we proceed, it might not be a bad idea to get a handle on the algebra. I have not discussed the algebra in detail. So for example, by using, the exact expression for the 1D classical Ising model's partition function, which we have discussed at length in the previous lecture. You take that expression, put it back in here, and perform all the required algebra and show that you actually get the same answer as you did from elementary considerations of the qubit. That would be a very nice exercise for you to familiarize with the math that is behind all this. Okay, let me tell you what is the main lesson that we have learned. So the main lesson we have learned is that associated with the zero-dimensional quantum system with some coupling constant, there is a one-dimensional classical system in equilibrium, but with a different coupling constant. The coupling constant of the classical system is related to that of the quantum system. So you see a very nice insight you can get from here. So the 1D classical Ising model is related to the quantum Ising model, the quantum qubit model in 0 dimensions. You see, the qubit model has finite set of degrees of freedom, so it cannot have any phases and phase transitions and so on. So now you realize why the one-dimensional Ising model does not have a phase transition, because it's just some physics of the qubit model that is there in that. Okay, so we can make these insights very precise in the following way. Suppose instead of thinking of beta, think of fixing delta tau. So delta tau is, let's say in some language, some small number. Now I can think of beta, that is the inverse temperature of the quantum problem, as n tau times delta tau. How do I interpret n tau now? N tau must be the number of sites in my equivalent classical problem. Remember, once I fix delta tau, k, the coupling constant of the classical problem, is fixed by tan h delta tau h is equal to e to the minus 2k. So that is fixed for me. So choosing delta tau and h fixes the coupling constant k, and if I now run n tau going to infinity, I am going to the thermodynamic limit of the classical system, and beta is going to infinity. That means the quantum problem is going towards 0 temperature. But we know that when I have a finite h, positive, let's say, I have a unique ground state for the quantum problem. So what this tells you is that when I have some coupling constant k in the classical problem, there is a corresponding quantum problem which has a unique ground state. That means the probability distribution or the partition function of the classical problem must also be describing a unique state. This is why the one-dimensional Ising model does not break symmetry at a finite k. So you can see that this is a very interesting insight that we are seeing, and we are seeing connection between classical and quantum problems. Okay, so I think it's a good time to revise or summarize what we have seen in the discussion today. So quantum systems in equilibrium are described by some Gibbs density matrix e to the minus beta h. The qubit is the simplest quantum system with two states. The qubit has an analytical free energy. It's just got finite number of degrees of freedom, if you like. So everything is nice in the as a function of the parameters, and therefore we don't expect any phase transitions. And the partition function of the qubit is related to the one-dimensional classical Ising model. Equilibrium state of a zero-dimensional quantum system is related to equilibrium state of a one-dimensional classical system with a different coupling constant. And this allows us to infer both ways. I can infer something about the classical system from the quantum system and vice versa, as you will see later. Okay, I hope you find all this very exciting, and if you haven't seen this before, you should definitely be very surprised by it. So in case you have not seen this before, I encourage you to listen to this lecture again and work through all the details. So next, since we have seen zero-dimensional quantum systems, the natural next problem to look at is a one-dimensional quantum system. We will construct a one-dimensional model, and we will have quantum mechanics, and we will see what is the physics that those models contain. So I'm sure you will join me for the next lecture. Thank you.